Hi guys, we now know the anatomy of external as well as medial in detail. So today we will be learning about the structures which are seen medial to the medial. What is that? Is the inner ear. This inner ear houses the delicate structures which are responsible for hearing and equilibrium. No wonder it is being covered by the toughest bone in the body. And what is that? The otic capsule. And this otic capsule is seen within the petrous part of the temporal bone. Okay, it is seen within the petrous part of the temporal bone, and this petrous part of temporal bone has got two slants, the anterior as well as the posterior slant. It is within the anterior slant you have the bony labyrinth. Okay, now in the posterior slant you have the opening called the internal auditory meatus, and this internal auditory meatus on its fundus has got some structures which you have to know. The arrangement also you have to be familiar with. And what is that? You have the internal auditory meatus like this over here. Okay, and then you have the falciform crust here coming from here. Okay, and it is divided superiorly by the Bill's bar. Okay, you have the Bill's bar here. This is the Bill's bar. Now, what are the structures seen within this? Okay, superiorly towards posterior, you have the superior vestibular nerve and inferior vestibular nerve. Okay, that you can easily remember, right? And the branch of inferior vestibular nerve called singular nerve is also seen here. Okay, singular nerve. It goes on to supply the posterior semicircular canal, and it is this nerve which is supplying the posterior semicircular canal, which is being cut in singular neurectomy. Okay, because posterior semicircular canal is one of the most common cause of vertigo. It is the most common cause of posterior semicircular canal BPPV, and hence if it is recalcitrant, that is even after all sorts of therapy, if it is failing, then you can go for singular neurectomy. Why? Because the single most common cause of vertigo, the posterior canal BPPV, is being supplied by the singular nerve. Okay, singular nerve. So that's about superior and inferior vestibular nerve. Here you have the 7 above or 7 up above. Okay, 7 up and Coca-Cola. Okay, 7 up is the facial nerve. This is the facial nerve, right? Here you have the 8th nerve or the cochlear part of the 8th nerve. Okay, only the cochlear part of the 8th nerve is in here. Okay, so this is how the fundus of internal auditory meatus appears. Fundus of internal auditory meatus. You will be able to see the structures such as the facial nerve above. This is the facial nerve above, and here you have the cochlear part of the 8th nerve. Here we have the posterior, you have the inferior vestibular nerve, and also the singular nerve. Okay, singular nerve. In the singular foramen it is seen. Okay, it is seen within the singular nerve, singular foramen. Okay. And here you have the superior vestibular nerve. Now, what is the significance of this Bill's bar? It helps you identify the superior vestibular nerve. Okay, when you are going for a surgery of the superior vestibular nerve, for example, a vestibular schwannoma, to identify the superior vestibular nerve, you have to identify this structure, the Bill's bar. The structure is seen posteriorly is the superior vestibular nerve, and it is the facial nerve. And the word Bill's bar is derived from the word William House. Okay, William House is the father of neuro-otology, and his nickname was Bill. Okay, William was called Bill, and from that he gave the name Bill's bar. Okay, Bill's bar. And who is this William House? This is our house MD. Okay, no, this is not William House. He is William House. William House is the father of neuro-otology. This is a question which has been asked. Okay, so it is important that you remember. He is the father of neuro-otology, and he invented the cochlear implant? Okay, cochlear implant was invented by the father of neuro-otology, Mr. William House. Okay, so that's about the various structures within the internal auditory meatus. Now coming to the development of the inner ear. How does the inner ear develop? First of all, you have to know that the inner ear consists of bony labyrinth as well as the membranous labyrinth. This membranous labyrinth is seen within the bony labyrinth. Within the membranous labyrinth you have got endolymph, and within the bony labyrinth you have got perilymph. Okay, the composition of both are different. The endolymph is high in potassium and low in sodium, whereas in perilymph it is sodium which is high and potassium which is low, because this perilymph is an ultrafiltrate of CSF, whereas endolymph is being secreted by stria vascularis in the cochlea and the dark vestibular cells in the labyrinth area. Okay, this is something which you have to know. That is, the endolymph is being secreted by dark vestibular cells as well as stria vascularis, and the composition difference. Okay, there is increased potassium and decreased sodium in the endolymph, whereas the perilymph is an ultrafiltrate of CSF and there is more of sodium and less of potassium there. Now, how does this membranous labyrinth and bony labyrinth develop? It is the membranous labyrinth which develops first. It is developing from the ectoderm. It is seen as a thickening in the area of the posterior cranial fossa. You have a neuroectoderm, right? The neuroectoderm of the posterior cranial fossa undergoes thickening in that area, and here this thickening develops into an otic plug cord. Okay, otic plug cord goes within and forms the otic pit later on. Okay, otic plug cord forms the otic pit. It is seen in the area of the developing hindbrain, the posterior cranial fossa area. Okay, and then this otic pit invaginates inside to form the otic vesicle. Okay, otic vesicle. So it is from the surface ectoderm of the developing hindbrain. You have the thickening called otic plug cord. Otic plug cord goes in to form the otic pit. Plug cord goes in to form the otic pit, and from the otic pit develops the otic vesicle. Okay, otic vesicle. Now this otic vesicle, it is shaped like a designer balloon. Okay, you can shape it into different shapes. Okay, this otic vesicle divides into two portions. Okay, similar to how a designer balloon is getting shaped into different shapes, otic vesicle is first divided into two portions. What are they? They are the endolymphatic diverticulum and the utriculosaccular portion. It is from this endolymphatic diverticulum that the endolymphatic duct and the endolymphatic sac develops. From the utriculosaccular portion, which divides further into two, the utricular portion and the saccular portion. Okay, now the saccular portion further undergoes differentiation, and as you can see here, the saccular portion of otic vesicle forms the utriculosaccular duct. Okay, and then the cochlear duct is also formed by formation of a constriction between the saccule and the cochlear duct. And what is that? That is what is called the ductus reuniens. Ductus reuniens is the constriction between the saccule and the organ of cottae, which is seen within the cochlear duct. Okay, between the saccule and the cochlear duct you have the ductus reuniens. Okay, and how does the three semicircular canals and the utricle develop? They develop from the utricular portion by differentiation, just like this. And while differentiating, the superior and the posterior semicircular canal join together and forms the crus communi, or the common crus. Okay, so the three semicircular canals opens into the utricle via 5 opening and not 6 openings. Okay, they open via 5 opening, where the superior and posterior has got a common opening the non-ambulated ends of the superior and posterior semicircular canal join together to form the crus communi, or the common crus. Okay, and that opens into the utricle, and similarly the ambulated ends also open into the utricle. Okay, so into the utricle the 3 semicircular canals open via 5 openings. Okay, 5 openings. Now coming to one of the questions that was asked, fetus starts hearing by what time in intrauterine life? Okay, by 20 weeks itself the fetus will be able to start hearing, because by that time the development is almost complete and they will be able to hear. But it is by 25 weeks the development of cochlea is completed. Okay, development of cochlea is completed only by 25 weeks. Okay, now what happens when the development does not occur properly? First of all, there is one anomaly. Who is this? Is none other than Michael Jackson, right? And this Michael Jackson, why did I keep his picture? Because Michael's aplasia is an anomaly where the whole labyrinth does not develop. Okay, what is that called? It is called complete labyrinthine aplasia, or the Michael's aplasia. Okay, Michael's aplasia. Here you can see the ossicles are developed properly, the ice cream cone appearance is present properly. Okay, but there is no labyrinth developed. Okay, so it's what is called the Michael's aplasia, or the complete labyrinthine aplasia. Okay, now if the 2.5 turns of the cochlea does not develop, instead only 1.5 turns of cochlea develop. Okay, if only 1.5 turns of cochlea develop, then that is what is called the Mondini's dysplasia. Okay, Mondini's dysplasia. Okay, now if only the basal turn of cochlea develops, what is that known as? If only the if the basal turn of cochlea fails to develop. Okay, if the basal turn of cochlea fails to develop, that is what is called Alexander's aplasia. Okay, Alexander's aplasia. And we also know in detail about the Sheeby's dysplasia, right? In Sheeby's dysplasia, what is happening? The cochlea and saccule fail to develop, and it is the most common anomaly. Sheeby's dysplasia is the most common anomaly. So we have learned about 4 anomalies. What are they? First, the Michael's aplasia is complete labyrinthine aplasia. Okay, the whole of labyrinth does not develop. Then you have the Mondini's dysplasia. Here 1.5 turns of cochlea develop. Alexander's aplasia, when basal turn of cochlea fail to develop. Okay, basal turn fail to develop. And finally you have the Sheeby's dysplasia. Here cochlea and saccule fail to develop. Okay, cochlea and saccule fail to develop. That's called Sheeby's dysplasia. So these are the various anomalies in inner ear development that you have to learn. Okay, now how do you identify which semicircular canal is which? Okay, you know there are 3 semicircular canals which are opening into the utricle, and then the utricle is connected with the saccule via the utricular duct, and the saccule is connected to the cochlea via the ductus reunions. All these things you know. Okay, and these are arranged within the bony labyrinth, as you can see here. So in the bony labyrinth you have the 3 semicircular canals, and this bony portion where you have the utricle and saccule is called the vestibule. This is the vestibule, and then you have the bony cochlea here. Okay, within the cochlea the portion which is of the membranous part is the scala media. Okay, or the cochlear duct. Okay, scala media is the same as the cochlear duct. Okay, now as you can see here, this picture is how the in real life when you are dissecting the petrous temporal bone, if you are looking for the semicircular canals, it will appear like this. Okay, this is the bony canal that you will be able to see. You won't be able to see the membranous part. Okay, so where will you see it like this? If you have the mid layer here, mid layer will be kind of like this, right? This mid layer you have like this. Okay, on the mid layer you have the round window in the area of the postero-inferior part, and you have the oval window above that. Okay, and you have the promontory here formed by the basal turn of cochlea. Here you have the promontory. Here is the bulge of the lateral semicircular canal, right? And just below that you have the facial nerve going. Okay, facial nerve will be going like this. Okay, so the part which is bulging into the mid layer is the lateral semicircular canal, that you already know. In the anatomy of mid layer we discussed how lateral semicircular canal dome projects into the mid layer's medial wall. Okay, that you know. Now the part which is projecting upwards, that is the superior semicircular canal. As the name implies, superior semicircular canal projects upward and it forms a portion in the skull base called the arcuate eminence. Okay, it forms a projection called the arcuate eminence. Okay, arcuate eminence. Now the superior semicircular canal and the posterior semicircular canal, they are non-ambulated ends are joined together to form the common crus or the crus communi. Here you have the crus communi. Okay, so from the lateral semicircular canal, posteriorly you have the posterior canal. Okay, that is towards the mastoid you have the posterior semicircular canal. Okay, the canal which is seen towards the mastoid is the posterior semicircular canal. Okay, so this is the ambulated end going into the vestibule. This is the lateral semicircular canal. Okay, now where else have you heard about vestibule? Vestibule is seen also in the nose. Okay, not just the nose, it is also seen in the oral cavity. You have another vestibule. In the larynx you have another vestibule. So in ENT itself you have 4 vestibules. Okay, so don't get confused between these vestibules. In the inner ear, vestibule means the part of the bony canal, the part of the bony labyrinth which is seen housing the utricle and saccule, that is the vestibule. Okay, so the part of the semicircular canal which is projecting into the medial wall of mid layer is the lateral semicircular canal. The part which is projecting into the mastoid is the posterior semicircular canal, and which is projecting upward into the skull base to form the arcuate eminence is the superior semicircular canal. Okay, so that's about the bony labyrinth. In the bony labyrinth you have got the membranous labyrinth. Okay, and here the membranous labyrinth you have got the membranous semicircular canals like this, and within that you can see how they are projecting into the utricle. Here this is the utricle, and here you have the saccule, and here you have the connection with the cochlea which is called the ductus reunions. Okay, that's the ductus reunions. So now you know how it is, right? You have the lateral semicircular canal here, sorry, the posterior semicircular canal here. This is the superior semicircular canal. They both join to form the crus communi. Okay, and all these are at an angulation of 90 degree with one another. Okay, 90 degree with one another, and the angulation between these semicircular canals is known as, I had already told you, what is that? It's called solid angle. Okay, solid angle is the angulation between the semicircular canals. Okay, so all these are joining into the utricle, and you have the saccule here, and the saccule is connected to the cochlea. You have the cochlea here, and from the utricle and the saccule comes the utricle and the saccular ducts, which join to form the utricular saccular duct, and which continues as the endolymphatic duct, and finally it forms the endolymphatic sac. Okay, endolymphatic sac. Now within the utricle and saccule you have a set of receptors, and within the labyrinth, that is the semicircular canals, you have got another set of receptors. Now what are they? The structures within the semicircular canals are seen within the ambulated ends of the semicircular canals, and they are called the crista ambularis. Okay, within the ambulated ends of the semicircular canals you have the crista ambularis. So crista is the receptor in the canal, C for canal. Okay, C for canal. And within the utricle and saccule you have the statoconia on the macula. Okay, macula is the receptor for this utricle and saccule. Now what is the function of this utricle and saccule and that of the semicircular canals? The semicircular canals deals with the angular acceleration. Okay, when you are moving your head like this, okay, the angular acceleration that is occurring is being dealt with by the semicircular canals. Because these semicircular canals are oriented in different planes, okay, it is projecting into 3 different planes, right? So all the movements can cause simulation of each of these canals according to the movements. Okay, there are movements like pitch, yaw. Okay, all these movements can cause a simulation of these semicircular canals, and so it deals with angular acceleration, and the up and down movement and the forward and backward movement is being dealt with by the utricle and saccule. The utricle is about the horizontal movement, the movement forward and backward, and the saccule is dealing with the upward and downwards movement. Okay, now this is a picture showing how the saccule and utricle are seen within the vestibule. Okay, within the vestibule you have two recesses, the recessus ellipticus and recessus sphericus. Okay, in the spherical recess you have the saccule. Okay, within the spherical recess you have the saccule, and the elliptical recess you have the utricle. Okay, in the elliptical recess you have the utricle. Now if you look carefully you can see there is something written here. This is the orifice of the aqueduct of the cochlea. It is seen in the scala tympani. Okay, it is seen within the scala tympani, and the scala tympani and scala vestibuli are seen as a part of bony labyrinth, and the scala media or the cochlear duct is a part of the membranous labyrinth. Okay, and along with the utricle in the recess ellipticus you have an orifice of aqueduct of vestibuli here. What is this aqueduct of vestibuli? What is this aqueductus vestibuli or vestibular aqueduct? Okay, now I told you the membranous labyrinth is like this, like right, and outside the membranous labyrinth you have the ossification formed by the bony labyrinth. Okay, now to protect the endolymphatic sac you have a portion called the vestibular aqueduct. Okay, vestibular aqueduct, which is a part of the bony labyrinth. Okay, so this vestibular aqueduct is opening into the elliptical recess here. Okay, elliptical recess here, and this aqueduct of cochlea is a communication between the subarachnoid space and the scala tympani, and it opens nearer to the round window. This is the area of round window, right? Nearer to the round window in the area of scala tympani, the aqueduct of cochlea opens. Okay, so you have got some terminology which are confusing, right? The cochlear duct means scala media. Cochlear duct is the same as scala media. Okay, it is a part of the membranous labyrinth. Then you have the aqueduct of cochlea. Aqueduct of cochlea is different. Okay, aqueduct of cochlea is a communication between the cochlea and the subarachnoid space. Okay, that is different. Now aqueduct of vestibuli is a covering for the endolymphatic sac. Okay, so this is how it appears. This is the bony canals. Here you have the cochlea, you have the vestibule, and you have the semicircular canals, and in the corresponding membranous labyrinth you have the cochlear duct. Okay, cochlear duct, and you have the various structures like endolymphatic duct, endolymphatic sac. Okay, and here you have a picture combining all both these pictures. Okay, you can see the opening of endolymphatic duct and opening of cochlear aqueduct here. Okay, so this is the endolymphatic sac projecting here, and here you have the vestibular aqueduct. Okay, vestibular aqueduct. Yes, now you can see that the vestibular aqueduct is covering the endolymphatic sac, and this endolymphatic sac, where is it seen? It is seen intradurally. Okay, intradurally. It is seen between the endosteal and the meningeal layers of the dura, as you can see here. It is seen between the meningeal and the endosteal layers of the dura. So it is seen intradurally.